Okay, why don't we begin? So today's speaker is Dr. Enrico Camporeale. He received his PhD in space plasma physics from the Queen Mary University in London in 2008 with his thesis on kinetic aspects of solar wind turbulence. And following that, he went to Los Alamos where he did his postdoc. And then after that, he moved back to Europe and was a tenured research scientist at the Dutch Center for Mathematics and Computer Science in Amsterdam. And when he was there, he founded one of the first research teams focused on the use of machine learning in space weather applications. And then in the beginning of 2019, he moved to Boulder, where he joined the NOAA Space Weather Prediction Center, where he's working on the combination of machine learning techniques with physics-based models for space weather forecasting. And he's an editor of the Journal of Space Weather and Space Climate, and also of the book on machine learning techniques in space weather, and recently chaired the first machine learning conference in heliophysics. It was held last month. So his talk today is on machine learning and the gray box approach in space weather forecasting.
Well, thanks everybody for coming. I'm really happy to be here today, despite the snow and all the difficulties. So thank you very much for being here. Yeah, I'm going to talk about machine learning and what I call the gray box approach. And this is a list of collaborators which have been involved in some part of this work, of this talk. So let's start with the sort of the objectives and the take-home message in a sense. These are things that I'm going to touch upon during this talk. It's kind of a long talk. I hope I managed to get to the end within an hour. So I'm going to kind of talk about why is artificial intelligence. Oh, sorry. Yeah. One thing. I remember. Yeah. So sorry about that. So why is artificial intelligence so popular today? You might have heard a lot about AI in the news, and the one sentence answer is because it's actually changing our everyday life, and I'm going to show a little bit about this. And why should a scientist, why should everybody in this room care about machine learning, and why I believe that at least a very basic understanding of deep learning and what a neural network is, why is this indispensable to the modern scientists, so to say. And the short answer, in my opinion, is because machine learning is really changing the way we do science. It's already happening today, and it's going to happen more and more in the future. And finally, what is a gray box approach, in my opinion, is our best bet. And I'm going to explain what the gray box approach is. So you might be familiar with artificial intelligence to some degree. It's has a long history, and for some time already, since the 60s, it has been the next big thing in a way. So this is kind of the popularity in time. There have been in the 70s and in the 80s what are known as AI winters, which are due essentially to so winters basically mean lack in funding and loss of interest because the kind of expectations of AI were not met. Sorry, I have kind of hard time talking with this microphone in my ears. So I have to say, these winters, or the whole hype and winters and booms were due more to the news or to the media attention more than to what the scientists were saying. And this is an example of New York Times from 1958. And you can read this. So this was at very much of the hype, or the first hype, or before the first winter of AI. And this says that the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, whatever that means for a computer to reproduce itself, and be conscious of its existence. So I will argue that it's mostly due to the this sort of wrong media exposure that we got this winter. So the first winter happened in the 70s, and they actually saw especially in the UK, there was this Lighthill report. Lighthill was a very well-recognized scientist in UK, and the parliament asked him to write a report about the status of artificial intelligence. And basically, his bottom line was that the general purpose robot is a mirage, or was a mirage at that time. And that was basically the reason to cut completely AI funding in England, at least, probably other parts of the world. And this is why there was this winter. Then, of course, AI reached new popularity, new high expectation, and another winter in the 80s. And now it's kind of on an explosive growth path. And talking about media sensationalism, this is just a few headlines of recently, from a couple of years ago, of what the news says about AI, and you can pick up your favorite. These are all really sensationalism in the sense that don't really reflect what is the status of the real AI research. So they promise to tackle Alzheimer, to replace doctor, to study mammograms. Will machine learning make you a better manager? This is recent. It's AI is inventing a new language that humans cannot understand. And my favorite is this one. AI could predict when you die. So there's no no more surprises there. It just tells you, this day, this year, you will die, and that's it. Then on the other hand, and partly because of this media sensationalism, but also because in recent years there were some true success, there has been an increase in funding in the last 5 or 10 years, and this doesn't show very well. So this is the venture capitalist funding in US in the last, I believe, 10 years, and it starts basically from zero, and this goes to 2017, I think. It's up to $5 billion a year. This is private investment in AI. And recently, in February this year, the president signed an executive order about maintaining American leadership in artificial intelligence. So the federal funding for next year for non-military AI application is about $1 billion. And of course, there's been arguments, especially from representatives from the industry, Intel, NVIDIA, and so on, that says that 1 billion is far from enough for actually having some good progress in AI. And they might be right, considering that Microsoft itself is investing the same amount of money, or even more. This 1 billion was just to acquire OpenAI, which is a non-profit foundation in San Francisco. And then on top of that, of course, what the American leadership is worried about is that China has promised to become the leader in AI by 2030 and is investing a lot of money. And just by a merit of figure, the city of Beijing itself, only the city of Beijing, is investing $2 billion, so twice as much as the American government, to fund the AI research park. So why there's all this attention to AI and machine learning in recent years? What has changed with respect to the 60s or the 70s or the 90s? You pick your favorite moment of hype in AI. Well, first thing is it actually works. It didn't work so well until 5 or 10 years ago. And then there are these 3 enabling factors. One, and this is a slide that I actually borrowed from internet. It is not even so recent. I'm not sure you can actually read the numbers. But there are basically these 3 enabling factors. One is the big data. We're all familiar with this phenomena. It has been said that 90% of the data available on internet, for instance, has been created in the last 2 years. So it's really an explosive growth. And aside from the size of the data, of course, is the cost of the data. And this one plot shows the dollar per terabyte in the storage cost. And probably can't read it. So it says that in 1980, 1 terabyte of data, that of course nobody had 1 terabyte of data, would have cost $14 million. And now I think with $100 you can buy 4 or 5 terabytes hard drive. So there's been a rapid decline of cost of storage. And then also the cost of bandwidth, because once you have a large amount of data, you also need to be able to move it around. So I'm not sure, again, the actual numbers here. It says today is $5 per megabit per second. In 1998 it was $1,200 per megabit per second. So big data is, of course, a important enabling factors. The second one is CPU and, more recently, GPU computing. So this chart here shows the theoretical gigaflops per second. This is also not very updated. It only goes to 2012. And the GPUs are basically growing faster than Moore's law in the last 10 years. And the cost, where is it? It's this one. The cost per gigaflops went down. So here it says in 2010 was about 50 cents per gigaflops. In 1960 was 1 billion and whatever. So, so the fact that the GPU computing has grown so much is a second enabling factors. And then the third fact is that IT companies like Google, Microsoft, Facebook have invested a huge amount of money in AI in the last 10 years. And this has, the result of this is that there's open source software, like for instance, TensorFlow is an open source platform made by Google. PyTorch has been made by Facebook, and so on. And there are cheap AI platforms as well. So these three enabling factors basically mean that today is easy and cheap even for a layman, actually, to run a machine learning model or method. So because of this, actually, we use, whether you recognize it or not, we use machine learning and artificial intelligence in our everyday life. Just whenever you use your smartphone, basically you use some sort of machine learning. These are just few examples. PayPal, or whenever you do online banking, there is some fraud. There's some algorithm that recognize whether this transaction is fraudulent or not. Recommendation system, wherever you buy a book on Amazon or you watch a movie on Netflix, there's a recommendation system that tells you, look, this is the movie you want to watch because you're going to like this, or this is the book you want to buy. And of course, there's a machine learning algorithm behind that. Something which might be more relevant to us scientists is Google Scholar. I don't know if you use this. I use it pretty frequently, the recommendation system. So this tells you which papers are relevant to your work. And I find fascinating the fact that most of the time, the papers that are recommended to me are actually relevant to my work, are either relevant to other papers that I wrote or even papers that I've been reading recently. And so this is pretty accurate. And then Uber has also invested a huge amount of money on machine learning. Logistic, finding the best route from point A to point B in traffic is all machine learning. One of the nicest application, at least for a foreigner living in a foreign country, is the translation, either text to text or text to speech or speech to text, whatever way you like it, kind of real-time translation. And then there are, of course, more futuristic technologies, like, of course, self-driving cars or trucks. Or this is actually a prototype which is in a few cities in the US is actually active. You can order your pizza or your groceries online, and there is a self-driving vehicle that brings it to you. So I'm going to spend a few minutes now showing couple of the biggest breakthroughs in machine learning. And these are entered in the history of AI, basically. And this is one of the reasons why AI has got so much attention recently. So one is the ImageNet classification challenge. ImageNet is a data set which has been put together in about 3 years' time using this Amazon Mechanical Turk. So this is a way, it's an Amazon platform that allows you to crowdsource easy tasks like classifying images. So about 50,000 workers have been worked on this from several countries in 3 years. And ImageNet is basically a data set of about 15 million images that belong to, so each one of these images is categorized in one of among 20,000 categories. So this goes from, everything, basically dogs. And it's because there are so many categories, it's not just generally, this image is a dog, but it's this breed of dog, it's very specific. And then after they collected this large data set and this huge amount of money of work to classify, to label, so each image is labeled with what the image is, they ran the challenge since 2011 to 2016, and the challenge is basically you get a bunch of these images to train your network, and then you get other images that you have not been shown before, and the challenge is to attach the right label to the right image for 100,000 of images or so on. So it is thought that there's a human, so the classification error, if you give this task of classifying images to a bunch of people, on average, 5% of the classification is wrong. Because some images might be, it might not be clear what kind of dog it is, might be blurry. So different people may actually attach different labels to the same image. And it is believed that the average error is about 5%. So when they started running this challenge in 2011, the error was about 26%, so it was much worse than the human classification. Then from 2012, they started, so this is already a large drop, and from 2012 onwards, they started using deep learning, while here it was more of a kind of system expert algorithm. And consistently from 2012 to today, basically the error has decreased up to the point where in 2015, it has been claimed that deep learning, so this was down to 3.6%. I think now it's about 1.5 or 2%, the classification error. So it has been claimed that deep learning can actually now perform image recognition with superhuman accuracy. And this is basically the holy grail for all the artificial intelligence research, is to perform a task better than a human can do at what they say superhuman accuracy. Second big breakthrough, which in my opinion is even more interesting, is AlphaGo. So you might or not be familiar with the game of Go. Is an ancient Asian game which has been played by, I don't know, 2,000 years or so. It's very popular in Korea and China, less so in Western countries. It's basically a board game. And it's much more complex than chess, for instance, because the number of combination you can play. So first of all, the board is bigger, 19 times 19. Number of combination is exponentially large. So in 2016, a computer software called AlphaGo, which was developed by a company called DeepMind, which is now owned by Google, played a game against Lee Sedol, which is believed to be it was the 18-time world champion, so it's the best player in the world. Himself, Lee Sedol, before playing the game, he was very skeptical that he would have lost against the computer. They played 5 games, and the computer won 4 times out of 5. So this was a kind of a milestone in AI, because it was believed that the game of Go was too difficult to be played by a computer. And what is more interesting on top of that is that the computer, while playing, discovered some new strategies that were not, at that time, was not understood by the experts. So basically, the cumulative knowledge of humankind of 2,000 years of playing this game has been beaten by a computer that was able to find some strategies that were not known or not even understood at that time. Then DeepMind didn't stop there, so this was already a huge, so they got the cover of Nature, and it was a huge success and news. Then recently, 1 year later, actually, they tried a different thing. So this AlphaGo was basically a machine learning algorithm that was trained including some human knowledge, meaning that basically the game was playing against a professional player many times, and in that way it improved itself. What they tried next is to train an algorithm from tabula rasa, meaning with no human knowledge at all. And what they did is to train this algorithm for, so basically the software plays the game against itself many times and improves. So it has been playing for 40 days, trained on 29 million games. And at the end of it, once it was trained, basically they played this improved version of AlphaGo, which is called AlphaGo 0, because basically it starts from 0, against the one that defeated the world champion. And AlphaGo 0 won 100-0. So this is now the best Go player in the world, and no human can possibly win again this computer. So I've been talking about like 25 minutes now about artificial intelligence, and sure, it looks great, but can we, as physicists or scientists, use it? And of course, physicists have a long history of borrowing great ideas from math. Machine learning, at the end of the day, is just a sophisticated statistical tool. It's a mathematical tool, nothing more than that. This is an interesting quote from a paper that appeared in New Scientist several years ago. This was kind of a historical recounting of how Einstein got to its relativity theory. And it is believed that Einstein actually didn't have a good grasp of 19th century geometry, like the work done by Minkowski and Riemann and so on. And at least in the author's opinion, if Einstein had understood 19th century geometry, he would have got his two theories of relativity sorted out a lot sooner. So this is kind of shows that, yeah, it's good to know what from physicists or scientists what is happening in math and applied math. So is there anything we can use in space physics, for instance, to improve our models, to improve our understanding, or to get faster approximations? So the answer is yes, of course, and there's been a few examples recently of using machine learning in science. One of the most interesting, in my opinion, is this one. You might be familiar with the Kepler telescope. They've been using Kepler to identify new exoplanets, and a couple of these new exoplanets have been identified using deep learning on this large catalog of events. Similarly, artificial neural network have been trained and used to discover hypervelocity stars from a catalog from Gaia. And also recently, now they're trying to find gravitational wave from the LIGO data, again using deep learning. So these are just three examples of where deep learning has been very successful in science or helping scientists to discover new things. So I'd like to spend a few minutes now introducing and explaining what is a neural network, because this is, first of all, I believe that every scientist at least, should have, as I said at the beginning, at least a very basic understanding of how a neural network works. And also because neural network is basically the core of all this deep learning achievement. At the bottom of it, there's always a deep neural network. So this is the typical example of the simplest neural network. Then, of course, you can have a much more complex architecture. And this is what it is, really. It's this equation, basically, is what the neural network does. And there's a bit of a nomenclature here. So you have a d-dimensional input, x. This d-dimensional input is multiplied by weight wji. So these parentheses here, so each one of these circle here is called a neuron. So you have m neuron, and in principle you have k outputs, even though in generally speaking, people tend to work with just one scalar output, but in principle this can be generalized to k outputs. So all you do is the following. You take your input, you multiply. So this parenthesis here is just a linear, it's a matrix vector multiplication, basically. You rescale your input, you add a term which is called the bias, and you end up with this parenthesis and in each one of these neurons. And then you feed these into H, and H is a nonlinear, what is called an activation function. This is really the core of the neural network, is the fact that you're using a nonlinear activation function here. So H of this object here now is the output of each one of these neurons, and then you play the same game. You multiply this by another weight matrix, W2, and you collect all of these into these neurons here. You sum another bias constant term. And then in principle, you can feed these into yet another function sigma, which can be a linear or nonlinear activation function. But the crucial thing is that H is nonlinear here. So one might wonder, why are you interested in doing this kind of complex approach of taking an input, multiplying, feeding into a nonlinear function, then multiplying again, and so on? Is it because these are the two of some of the most fundamental theorem in neural networks came up in the early 90s. And basically, what this theorem or paper and show the theorem says that if you you can actually approximate any nonlinear function by a superposition of sigmoid function. So if this H here is a sigmoid function, I'm going to show in a moment what that means. With this construction here, assuming that you have enough number of neurons, meaning that this summation is large enough, you can approximate any nonlinear function to any degree of accuracy. This has been shown by these several theorems, actually. So basically, the neural network is a universal function approximator. You can approximate any function. Let me give you a sort of very basic, actually intuitive explanation, because at least to me, it's not clear why just superposing sigmoid function, you can end up with any nonlinear function. This is, again, a simple example. Let's assume you have these 5 points at this fixed x location and this y. And let's say that we want to use a linear combination of step functions. So the easiest sigmoid, so sigmoid is a function that goes basically, it looks like an S, from 0 to 1 with a sort of a step. And the easiest you can think about is the Heaviside function. So Heaviside is 0 for x less than 0 and 1 for x greater or equal to 0. It's the classical step function. So you can see that having a Heaviside function of x plus 3/4, having 1 minus this object here already gives you this approximation. This is easy to see because basically when x is smaller than minus 3/4 here, h is 0, so you have 1. And when x is larger than minus 3/4, this becomes 1, so you have 1 minus 3/4, and this is so this is the result of this approximation here. So you already got basically 2 points. And then you can play the same game and add another Heaviside function centered at x plus 1/4 to get this other step here. And then you keep playing the game. You add another Heaviside function at x minus 1/4, and you get this step here. And you can do this for any number of points. And basically what you get here with only 1, 2, 3, 4 Heaviside function plus a constant is basically a 5-point step approximation of a parabola. So these points here were chosen to be on top of a parabola. And again, at least from an abstract point of view, you can think of extending this to any number of points. Now, of course, if your activation function is a Heaviside function, you will always end up with something which is discontinuous, which you might not want. So what has actually been used as an activation function in neural networks is not the Heaviside, although this was used in the 50s or 60s in what is called the perceptron. But in more modern neural network, you actually use something like a hyperbolic tangent, a tan h, which looks very much as a Heaviside function, but it's continuous. So basically, if you use the tan h, then your neural network, at least this simple neural network with just one layer, looks like this. You take the tan h of x multiplied by some weights plus b. So you feed this into the tan h. Then you multiply this by another weights, and you sum another bias term. So one question, just to, again, to play with the idea and to just give an intuitive explanation of how a sum of tan h can give you any function. So how many, so if, say you want to approximate, again, this parabola, but now in a continuous way from -1 to 1. So how many neurons, meaning how many tanh of something you need to sum up to have an accurate approximation of a parabola? And of course, modern neural networks have hundreds or thousands of neurons, or millions even. But this is just a simple example. And so the question is, how many tanh do you need to approximate a parabola? What do you think? Well, more than one, right? Tanh doesn't look. Yeah, that's a good point. So how accurate? I mean that by eye, by your distance, you wouldn't. If I plot one on top of each other, you wouldn't notice the difference. That's how accurate I mean. Less than 10? That's right. Half a dozen, which is less than 10. Yeah, even less actually. So the answer is 2, only 2. And so the black line here is the original parabola, and the blue line is the shifted tanh, so it's tanh of ax plus b. And these actually do not look much as tanh, but if I zoom out, you can recognize that these are actually hyperbolic tangents. And if I take the sum of these two, this is what I end up with, which of course is not very accurate. So my task was only to do a good approximation between -1 and 1. And if I zoom in again, you can see that it's pretty accurate. And this is very surprising, at least to me. It's not intuitive at all that you can sum 2 tanh and get an x square. So to understand how come that the sum of 2 hyperbolic tangents can approximate so well a parabola, I guess the only way, or one of the best way, is to look at the Taylor expansion. Every time you want to approximate one function with the other and understand how good that approximation is, you take your Calculus 1 textbook and you look into Taylor expansion. So now you might not remember, and I don't remember for sure what is the Taylor expansion of tanh, but one thing that is a kind of strange is that tanh, even if you don't remember the Taylor expansion, you know that it's an odd function, right? And what does it mean that it's an odd function? It doesn't mean that it's a strange function. It means that the Taylor expansion only has odd coefficient, like x cubed, x to the 5th. So how comes that the sum of 2 functions which are odd can give you something which is even? And it's pretty simple, actually. It's because if you take it's because you shift the function. So the tanh of ax plus b will have something which is ax plus b cubed, which when you expand that will give you some x squared. And in fact, if you are lazy and you want to do the Taylor expansion yourself, you use Wolfram alpha, and you ask, what is the Taylor expansion of tanh ax plus b plus tanh minus ax plus b, which is exactly what these two things are. And it turns out that the dominant term is x squared. So the expansion of this guy here is, you probably can see that it's tanh of b, which is just a constant, is a number, minus 2x squared times something. So the dominant term in this expansion is actually x squared. So that's cool, right? At least it's cool to me. This was just a kind of to give you an intuitive explanation on how you can play with superposing sigmoid function and end up, of course, this is just a local approximation of a simple function, but you can extend this idea, at least in an abstract way. And this is why this theorem showed that the superposition of sigmoid can actually give you any nonlinear function. And this is really the strength of neural networks. So let's move on after half an hour that I've been speaking kind of randomly about AI, about space weather and space physics. I recently wrote this review, which came out on space weather, about the challenge of machine learning in space weather. And this is a histogram I put in this review, showing the number of publications dealing with space physics or space weather and machine learning. At least the paper that I reviewed in this paper here, going back to 1995. It was very interesting to see that in 2018 there was a huge jump of number of papers published on the topic. I would be interested to see whether this keeps going in 2019, 2020, or so on, or it was just a blimp. So what is machine learning for? How can we actually use it in our field? That's, I guess, it's what we're really interested into. I'm just going to give you a few examples of recent papers that have been used machine learning. And I'm kind of biased, taking from my own papers, I have to say. But there are a bunch of other papers. So one task is this supervised classification. So this is exactly the same task as was in the ImageNet recognition challenge. So you have a bunch of data you want to know, and you have a pre-specified classes, and you want to know this data point in which class does it belong. Is it a cat or a dog or whatever? And we use this for solar wind classification. So there's this idea by Joe Borowski, he published a couple of years ago, that basically he can divide the solar wind in these 4 classes based on the origin on the sun of where the solar wind comes from. So there's ejecta, coronal holes, sector reversal, and streamer belt. So what we did is to basically take, so first of all, he manually labeled 8,000 hours of data. So for these 8,000 hours with this kind of human knowledge expertise, you can say that this 1 hour belongs to ejector and this 1 hour belongs to coronal holes and so on. Then we use these attributes, and we've been using the Omni dataset for this, so it's an hourly frequency. The solar wind speed, the proton temperature, standard deviation, the sunspot number, solar radio flux, Alfvén speed, the proton entropy, and the temperature ratio. And we use these as inputs to train our machine learning algorithm. In this case, we use something called the Gaussian process. We don't have time to go into the detail, but it's a very nice and powerful. It's not a neural network, but it's something very interesting. And this is the result of the classification. So what we did, we have this 8,000 hours. We cannot use all of it to train, otherwise we don't have any ways of validating our model. So what we did is to only use 10% or 15%, up to 25% of the 8,000 hours to train the model, and then check how our classification model works on the rest of the data. And this is the percentage of correctly categorized data points. And of course, it depends on how much data you use to train, but it's always kind of above 90 or 95%. So this is a very accurate classification system. And then what we did after we have trained this model is to classify all the rest of the data, which is about 300,000 hours from the 60s to nowadays on the Omni dataset. And I think this is interesting because then you can use, different origin of the solar wind or different types of solar wind have different attributes, and also different geoeffectiveness for space weather and so on. Second example is a completely different task. It's a more classical regression task. So you might be familiar with what regression is. Basically, the regression problem tries to answer this question: is there a general enough relationship between inputs and outputs? In other words, if you can find the relationship between a bunch of inputs and some outputs, you will be able to do some forecasting. And this, for instance, can be done in space weather to forecast geomagnetic indexes. And in this work, specifically, we focus on the DST index. So the DST is a geomagnetic index, which is basically takes into account, it's a proxy for the Ring current, because it takes into account the variation of the magnetic field along station on the equator. And it's measured in nanotesla. So in this work here, we used what is called long short-term memory neural network. So this is a specific kind of neural network combined with the Gaussian process, which is the same mechanism we used in the previous paper, to do forecasting of multiple hour-ahead forecast of the DST index. So I'm going to show you some results. So this is for one particular storm in November 2003. So this is how the DST looks like. Again, it's a nanotesla. Whenever you have a storm, basically you have a big jump downward of the DST, and it can go down to minus 400 or 500 nanotesla. So this is just 1 hour ahead, and to be honest, it's not that hard to make a 1 hour ahead prediction. The blue line is the true DST measured, and the red dashed line is the prediction you have 1 hour before. So here the correlation coefficient is pretty good, it's 96%. The root mean square error, which I believe is calculated over the whole data set, not just for one storm, is pretty small. Then we move forward. We do the 3 hour ahead, which is still pretty good, and even the 5 hour ahead. And this is, to me, it's pretty amazing, considering that, so now this dashed line here are 5 hours apart. So what this means is that whenever you have an observation at one given point on one dashed line, you do the prediction for the next dashed line. So basically, when you are here, you don't know anything, of course, about the future. You only have observation of the past. But the neural network already recognizes here that there's going to be a big jump down, which might not be perfectly aligned with the real value, but still gives you an indication that there's going to be a storm coming. And the same thing when you're here, it's going to predict these values here. And the most amazing thing to me is that at some point, when you are about around the negative peak here, of course the storm could keep going down. I mean, there's no reason why it should stop, unless of course there are some physical reason. But the neural network, when you are at this dashed line here, already recognizes that this is pretty much the bottom of your DST negative peak. So the next prediction gives you the recovery phase. So there must be some physical mechanism here that the neural network recognizes that the storm. Huh? To the change of the slope, maybe. But you see, even if whenever the slope hasn't changed already, so I mean, even when you're here, it already predicts this point here. So it already knows that it's going to recover. But I mean, that's a good point. You might see little slope changes. No, it also uses some external inputs like solar wind speed, BZ, and so on. Yeah, to just only use DST would be pretty hard. Yeah. So let me touch upon real quick on the gray box approach, which I promised at least in the title. This is one of my main interests now in using machine learning. So basically, the gray box, so in the kind of general classification of methods, one has white boxes approach, gray box, and black box. And basically, the white box is just using a first principle model or physics-based model. And the black box is using a neural network or whatever empirical model where you basically use a lot of data to train your model. In the gray box approach, as the word says, basically it's what sits a little bit in between. And you can use the gray box approach in different ways, at least 3 different ways. So the first is what we actually already do most of the time when we do physics-based modeling. We almost never work with a first principle model. We always do some sort of approximation, reduced model. We end up with MHD or whatever is your favorite reduced model. So the reduced model has a lot of physics in it, but also has a lot of free parameters that you can adjust and change your simulations, for instance. And machine learning can help in learning what are the optimal parameters that gives you the more predictability to your model, basically. Another way of using machine learning is to just take the first principle model and train a surrogate model, for instance, a neural network that gives you, so this is sort of a trade-off between accuracy and speed. So this runs much faster than a physics-based first principle model. It's not as much accurate, so the question is, what is the best trade-off between accuracy and speed? And then a third way, which I'm going to show an example if I have time, is the machine learning enhanced physics-based model, which means you take the outcome of a simulation, which might be accurate but not so much in all different cases, and you enhance this simulation by using machine learning. So I'm going to actually just show one example of this gray box model and this one, so 2 examples. So this is one of the best recent idea in applied math, and I can say this because I'm not an author of this work. It's a physics-informed neural network. There are now, this was one of the original paper came up in early this year, but now there are tens of different papers using more or less the same idea. So what is a physics-informed neural network? And what is a deep neural network? It's a pretty simple idea, actually. So as we said earlier, the neural network is nothing else than a nonlinear map between multidimensional inputs and some outputs. Also, something which is very important is that no matter how complex and how many layers and neurons, how many complex the neural network is, at the end of the day, it always will give you an analytical and differentiable function almost everywhere. So what this means, also I didn't really touch on how you train the neural network, but basically you train it as an optimization problem, meaning that you want to minimize a given cost function. And usually the cost function is this object here. You have some prediction of the neural network, and you have some data, some observation, and you want to minimize the distance or the L2 norm of this quantity. So this is the way, so this basically gives you the optimization problem by solving which you find the optimal weights of the neural network. So the idea of this physically informed neural network is because the function is analytical, you can actually derive exactly all derivatives. So for instance, if you want to solve a diffusion equation, this is an equation which is used at least as a first order approximation for radiation belt studies. It's believed that energetic electrons trapped in the radiation belt undergo radial diffusion. So this is a good, at least first order approximation of that process. And you can say, okay, I want this equation, I mean, this guy here to be 0 or as small as possible. So I put this term here in my cost function. And I train the neural network such that the output of the neural network will be f, the solution of the equation, but also DLL and tau, which are basically the two free parameters. So this is a diffusion coefficient, this is an electron time scale. In a sense, these are the two free parameters that enters in your equation. So we have been trying, at least as preliminary steps, to play with this idea of physically informed neural network. And we haven't got yet to the point where we solve this for real data, but the goal is to use Van Allen probes data at the end to verify, to validate the whole approach. So for now, I'm going to just show you some synthetic examples, which I think are still very interesting. So let's assume you want to have, to solve this equation. Again, it might be too small to see. So this is the time derivative of f minus 0.1, the second derivative in x of f, fxx, plus 0.5f. So this is a sort of simplified version of these, where basically the diffusion coefficient and the time scale are just scalar number. So we can solve this equation. So this is a two-dimensional equation in x and space and time. And this is the exact solution here. Then we can put some 1,000 scattered data points in this domain and train a neural network to solve this and to give us as output the f, the coefficients, and so on. And this is what the neural network identifies as the correct equation. So you can see there's a small discrepancy, but it's pretty small. So instead of 0.1, it finds out 0.099, instead of 0.5, 0.50, and so on. And this is the predicted f, which basically it's very close to the real one. Then we play with the second concept. We say, okay, but we don't really have, whenever we're going to use it with real data, we don't have scattered data over our domain. What we have is just one orbit, or actually two orbits of the Van Allen probes. So we play with these ideas, basically put in first one and then two orbits, and you can still see that the identified PDE is very close. So these coefficients are very close. So this looks like this work has been done by George Wilkie, which now is a PPPL. And this is a very promising idea that we're going to try and test with Van Allen probes. In the last example I'm going to show you on the use of machine learning is something I've been working now on NOAA in the last few months, and is about the BDT prediction. So the BDT is the rate of change of the magnetic field on the ground, which is important to be able to predict because it's responsible for the geomagnetically induced current, which is one of the main effects of space weather. And in the last 2 or 3 years, we have been at NOAA. We have this Geospace model, which is a physics-based model developed by University of Michigan. Basically, it comprises 3 different modules. It's a global MHD model, and then there's an ionosphere physics module, and the ring current or radiation belt module. And so these 3 basically physical simulation coupled together. This is an example of how does this look like for a given location, a high latitude. And the black line, so this is the BDT for some different MLT hours. The black line is the prediction of the physics-based model, and the blue line is the observation, the real data. And this data comes at 1 minute cadence. So you can see that the physics-based model, especially for large events here, is not able to capture this. This is also what is shown in these plots here. So these are 3 different stations at high, mid, and low latitude. And the horizontal axis is the BDT real, so the observation, and the vertical axis is the simulation, and the red line will be a perfect prediction. You can see, especially when, and this is in logarithmic scale, when you have large events, the simulation tends to underpredict the values. And this plot here shows so first of all, it has been recognized by the community, and it was already in this paper, that it's probably hopeless to try to predict the BDT at 1 minute cadence. So the problem has been recast in the following way. What is the probability that the maximum value of the BDT over a 20-minute interval exceed a given threshold? So this dashed line here are some predefined threshold, and so the question becomes, again, sort of a classification problem. What is the probability that for a given 20 minutes interval, the maximum DBDT will go above that threshold? And this is the true skill score for the physics-based model. Again, for 3 different stations. The true skill score is defined as it's one of the many metrics used for probabilistic forecast. It's defined as the probability of detection minus the probability of false detection. And you can see that especially, for large threshold, this goes down to 10%. But even when it works well, it never actually reaches TSS larger than 30 or 40%. So the idea here was to take the output of the physics-based model and enhance it with machine learning. This is what I've been doing, again, in the last few months. And if you're interested in the machine learning technique, what's under the hood here is what is called a boosted ensemble of classification trees, which has been trained over 20 years of data. And I don't really have time to, there's an interesting detail here because we don't have 20 years of simulation. So how to match the 2 or 3 years of simulation with 20 years of data, that's kind of a technicality we can discuss later if you're interested. And this is what kind of the bottom line of this work. So in horizontal line, there's the true skill score for the Geospace only. So this is the physics-based model only. And this is when we take the physics-based model plus machine learning. And the different symbols are for different station, and different dots are for different threshold. You can see that for every case, we get an improvement. In the most extreme case, we go from 20% TSS up to 70%. This is a large improvement with respect to the physics-based model. All right, I'd like to conclude. My time is almost over with, again, kind of citing myself. So this is the last section, last chapter of this review paper I was talking about. So basically, this paper was commissioned by the AGU editorship, and they kind of decided that the title would have been Challenges to Space Weather. So I thought I need to have a section about the future challenges. And I'm going to just list what I believe, this is, of course, my own opinion, are going to be interesting future challenges to use machine learning in space weather. So the first is the information problem. And this is kind of related to the question we had before. What is the minimal physical information that we need to train a model? Can we just use DST to predict DST, or do we need something else? And this, of course, is important for machine learning, but at the bottom of it, there's really a physical question. What is the causation or correlation between quantities? Then there's the gray box problem, which is what is the best way to make an optimal use of our physical understanding and and our large amount of data, so to match the physics and the data, what's the best way to do that? The surrogate problem, so especially in space weather, we have a chain of many different physics-based models that are with their own assumption that are valid in this specific domain. So there's this one that solves for the radiation belt, this one solves for the ionosphere, and there's a long chain of models. And of course, one might wonder what model components within the chain or within each specific model can be approximated by surrogate model, like neural networks, and what is an acceptable trade-off between the loss of accuracy and the speed up, right? You can say, okay, this model runs 100 times faster. It's not as accurate as the other one, but what's the best trade-off? Then there's the uncertainty problem, and this is yet another paper I've been working on recently. Because all of these methods basically have uncertainties related, because the input themselves most of the time are uncertain, how do we propagate the uncertainties through a given model? And is there a way? So this paper was actually about coming up with a way of generating probabilistic forecasts from the deterministic model. The reason being because most, if not all, of our model in space physics or space weather are actually deterministic. It's one input, one output, another input, another output. But you might want to have an estimate of the uncertainty of the outputs. This is a serious problem in space weather. It's the too often, too quiet problem. So the data are typically imbalanced, meaning that you have many, many hours where nothing really happens. It's quiet time, and then a few hours of storm. And it's really hard to train a machine learning model with imbalanced data. And then at the bottom of it, I think it's what we are mostly interested from the physics side is the knowledge discovery problem. Namely, how do we distill some knowledge? Once we have our machine learning model that works perfectly well, do we learn something from it? Can we extract some physical knowledge from it? Okay, this is my conclusion and suggestion for further readings. So in my opinion, machine learning has a great and will have a greater and greater impact on the way we do science. I really believe it's not because it's something I do. Maybe also I'm a bit biased, but there's no way to escape machine learning in the next future, and it will impact the way we do science. We look at data. The single case study paradigm, where you take your favorite PhD student and you say, look at these 100,000 hours of data and find the one case that validates my theory. That's not going to work anymore for much longer, because PhD students are not going to do that anymore. The black box approach is fine if you're just interested in the prediction per se, as we are many times in space weather. But if you really want to understand the physics, I think the gray box approach is more robust and might actually help us in improving our physical understanding of a system. So this is a book I've edited. It came out last year, which is basically a collection of different machine learning techniques applied to space weather. And this is not specific to science, but it's a very interesting reading. It came out from the Royal Society in UK. It's just a kind of overview of how machine learning will impact our society at large. Thank you. This thing. No, I take the output of the physics of the geospace, and I use that along with other quantities as an input for a machine learning algorithm, specifically classification trees. So does that? So I mean, besides from the detail of what ML algorithm you use here, any machine learning, I mean, whether it's a regression, in this case it's a classification problem, but this doesn't really matter. It's always, you get some input, you want to predict one output, right? That's the most general way of describing it. Now, if one of these input is an input which comes from a physics-based model, he has more values, or he has some values, we believe, because the physics-based model gets it right sometime. So I guess the ground level idea is among all the different inputs that I can use. For instance, here I use some inputs from the solar wind, right? So use solar wind at L1 from Omni to predict the DBDT 1 hour later, right? But you don't have any real time, you don't have what's going to be the future of the magnetic field on the ground, right? So I use the Geospace as kind of an approximation of that and use that quantity as an input for my machine learning algorithm. Is that Sure. No, no. I just run the model. In fact, I didn't run the model. This the Geospace model has been running from 2006 and it's all archived. So I just went into the archive. I took whatever is the output of the simulation, and I take this output as an input from my machine learning algorithm. So it doesn't change the physics-based model. You just take that as one block, one of many other inputs that the machine learning uses.
So what happens if there's a bias? It's really up. I mean, is your machine learning then getting in the wrong direction? How accurate does the American model have?
Well, it is biased because if it wasn't biased, I would assume that the true script score would be higher. This must be because there's some sort of, the bias or limitation you can call of the physics-based model is not able to get the largest storm and so on. But once this becomes just one of many inputs, the machine learning algorithm recognizes, no, I can trust this input for this condition, and I cannot trust this input so much for those conditions. So it kind of weights the different inputs in different ways. And so it's just the fact that we trust to some extent the physics-based model, right? I mean, you can use any input. Now you can use the expert and say, what is going to be the DBDT the next hour for this station? You give me a number. And if I believe that number is valuable, I put that number as an input to my machine learning. It's nothing more than that, really.
Well, this is a simple example. How many layers of neural you have and how long for you to...
Yeah, this is not a neural network. It's the classification trees, so it works a bit differently. It's it's a decision tree where you have a multidimensional input, and the decision tree basically partition your input space, because this is a classification problem, right? So for any threshold, any station, you have positives and negatives over 20 years of data, and the classification trees finds the optimal partitioning of your multidimensional input space such that all the positives and negatives ends up in the same subspace of your input. Is that
It's fast, right?
is it what?
It's pretty fast.
It's fast, yeah. It's fast. Yeah, it's faster to train. I would say that the neural network and all machine learning algorithms are, the training is really the longer time. Then when you use it to predict, it's super fast. I mean, it's just sort of it's a tree. I mean, it's just you have this number for inputs where you end up in the tree. This is 0. This is 1. This is 0. This is 1. That's how it works. Yeah.
So can you identify what parameter in the model was causing the problem after your film?
What parameter in the physics-based model mean? Or
Because basically you're having bias in the prediction of the model. You're trying to help correct that.
well, I'm not sure what you mean by bias. So by bias, yeah, I guess it's a bit of a nomenclature. So this is the prediction of the physics-based model. Again, the horizontal is the real data, and the vertical is the simulation. So what I would call a bias will be something which is, shifted. So for every value, it's always some quantity off. Here, I'm not sure if there's really a bias, because there's some region for which the physics-based model actually does a pretty good job. Then for larger events, it underestimates. So it's something which depends. It's not a constant value, right?
The bias may not be the right word, but I was wondering, what would cause you sometimes miss the
Yeah, that's really hard to say, because then you have to. Yeah, that would be a different project, probably, because then you have to look in. I mean, go here and look what are the inputs of the physics-based model, how those inputs.
right, because you're tuning some parameters.
No, again, here I didn't do anything in the physics. I just took the output. So what? Maybe to clarify. So the Geospace, what is operational. So this takes the values from Discover or ACE at L1 and uses this as an input to the MHD model to drive the whole simulation, basically. And then from the simulation, you can derive the DBDT. So if that doesn't work, I mean, there are myriad of causes why that wouldn't work. Is MHD valid?
I was wondering how to improve our model from this.
Yeah.
I think I have the same question, but I'm thinking of it just a little bit differently. It seems, so you've got the model input, and then you've got the other input that you're inputting.
Mm-hmm.
And you mentioned you might have a situation with your trusted model. So for example, you might be able to eliminate false positives where there are conditions where the model tends to predict something, but your machine learning determines that those conditions it tends to predict wrong.
Mm-hmm.
So what I think Tom is asking, what I was wondering was, can you actually isolate the situations in which this happens and understand where your model is most likely to fail and use it to improve your model? Is that sort of what you're getting at? Yeah.
Yeah, no, I see what you mean. I didn't look that much into detail. I guess we already know that the model fails when DBDT is large, right? So this already tells you that you have to look in all the situations where the DBDT is large, and therefore what are the inputs, the other inputs that tells you that the DBDT is going to be large, and in this case, distrust the model. So it's kind of reverse engineering of the whole thing. Yeah.
All right, thank you again.
Thank you.